Good afternoon, everyone. I'm the last talk, I believe, for the Diptera Session, and I'll just be giving you an overview of what we've been doing so far on invasion patterns and niche comparison of the hoverfly Toxomerus floralis between its native and non-native ranges. So just to give you an overview of hoverflies in general, it's about 6,200 species worldwide, 210 genera, with the highest diversity in the Neotropical region. In Africa, there's about 610 species, 60 genera, with 4 subfamilies. Syrphidae is mostly terrestrial, predatory larvae, and they're mostly prey on Diptera, the important predators of aphids. Well, of course, there's some exceptions. Syrphidae preys on Coleoptera and Diptera larvae, and then Allograptors are phytophagous leaf miners and pollen feeders. Now, Toxomerus has about 150 species globally. These have been historically confined to the New World, but they're most speciose in the tropics. Toxomerus floralis, it always gets me, has a native range in the US and Southern America. Jourdain et al. 2015, they reported it for the first time from the Old World, from the Afrotropics, and also described its feeding ecology, determining that it's pollen feeding. So then the question comes up, what's the ecological requirements for Toxomerus floralis and its natural history? Jourdain et al. 2015 observed Cyperus rotundus and Mesocarpus hirtus as localities, and actually determined that the larvae feed on both of this, and larvae and then the pupae are on these plants in the field. They also established both of these as host plants, or established that they are host plants rather. And so now the question is, how does the current known distribution of these species compare to the predicted potential distribution of the fly? So is there an overlap of contributing variables in the distribution of the host plants versus Toxomerus in the native and invaded ranges? So first, before we can actually determine that, I just want to give you an overview of what the host plant, what they look like. So the first one, the native range host, is the tropical girdle pod. Its native range is Mexico to tropical America, and that's as the exact same native range essentially as Toxomerus floralis. The realized range host in Afrotropics is cocoa grass or nut grass. It's native to Africa, southern and central Europe, and southern Asia, and it's been called the world's worst weed. So this is just a graphic to essentially show how the rapid invasion of the Florida calligrapha has actually spread from 2013 until 2024, and you can see it's been quite a rapid spread. So then how can we predict its potential distribution in Africa and beyond? To do that, we're going to attempt to use, or we actually have done it, species distribution modeling, and it's essentially a process of predicting the interactions between the species and the environment. It can also then be used to study the effects of environmental factors and other variables and species interactions on the distribution of the species geographically. It can also be used to identify areas of suitable habitats for species and to predict effects of climate change on species distributions, and then to inform future conservation efforts. So to do that, we first had to get distribution records. So to do that, we data mined GBIF, which then included also our naturalist records. We also included our own fieldwork records as well as museum records. And this just shows the native and invasive range distribution points. We then combined that with bioclimatic variables, which is based on weather stations, so it's these interpolated bioclimatic variables. And so when you've got that information, our approach is essentially to take the 632 records that we got from GBIF and from museums, and thin those in R at 10 kilometers to basically lessen the potential collecting biases, etc. And so we ended up with 323 records, 235 native, 128 invaded. For the bioclimatic variables, we did a principal component analysis as well as a variable inflation factor to determine if there's any collinearity between the variables. And of those, only 5 were retained. Those were the most orthogonal to each other, so that we could make sure that there was no collinearity between them. We also generated zero absences for these records, seeing as we don't have actual absence records. These were then combined in our with the package Biomod2, where we ran 12 different models. There's more like the standard models, which included things like MaxEnt, which a lot of us know, We then evaluated that with TSS, RSC, and Kappa, just to sort of evaluate how the single models performed. Those were then combined into ensemble models. Now let me just go back. For the ensemble models, essentially out of we generated 1,332 models for each of the native and then also for realized ranges. And of those, we only retained 108 for the native range, and for the realized range, only 32 of the single models were retained. Just to give a predicted distribution for the native range, with the median of probabilities modeling technique essentially coming out as the best performing. And you can just see that compared to, for example, the realized range. The realized range shows a much more sort of wider potential distribution in Afrotropics as well as in Asia. I'll come to that now, why we're then also looking at realized and not using just the native range to predict its potential distribution. Another one of the modeling techniques that came out quite highly performing is committee averaging. The problem with that is it's more of a yes-no result, so doesn't quite give a finer sort of fine scale where you can actually see where it's not a yes or a no. And so if we compare then the median of probabilities, you can see that for both the native range projections as well as the realized range projections, the current known distribution for the species is actually, it lines up quite nicely. There are still a lot of red areas where the species can potentially occur, and that's also potentially just due to we haven't gone to collect there, so we don't have those data points yet. If we then overlay the host plants, in this case Mycocarpus hirtus, you can see that there's quite a lot of overlap between in the ensemble model in the native and the realized range with the host plants. Same for Cyperus rotundus. There's quite a lot of overlap there as well. And if we then if we project that into Asia, you can see that Asia is quite, according to the models at least, very much suitable for invasion for the species. To further on, you did a Boyce index just to test for model performance, and both the native range and realized range models both scored above 0.98, so both of them performed quite well in terms of habitat suitability. When we then look at our variable importance as well, which with the variables were actually the most important seemingly for predicting distribution of Toxomerus floralis, you can see bio 18, bio 2. Bio 18 is precipitation of the warmest quarter, and bio 2 is the mean diurnal range. And so those two are the most contributing factors for model performance. If we then look at the response curves for those, it actually gives us a nice idea in terms of what potential habitat environmental restrictions are or climatic restrictions, sorry, for the species. With the species, we can see when there's difference in 10 degrees between the minimum maximums during of temperature, you can see there's quite a drop in species response. Similarly, when there's more than 500 millimeters of rain within your warmest quarter, you get it starts flattening out. That's sort of where the species does best, it seems. But anything lower than that, with lower rainfall, they don't seem to do much very well. Then we also did some niche dynamics just to see, sort of to test what niche conservation and just how essentially what the niches are between the native and realized ranges. And so what we found is there's minor to moderate overlap between the niches, but there was also then, of course, stability of 76.4%, but it's also niche expansion of 23.6% with less than 1% unfilling. So what this then essentially shows us is that the species can occupy new niches in areas that it does just move to, and that's also, of course, while keeping its initial niche, which means that's a typical of an invasive species. What we then also did was we tried to see what would happen if we use global climate models, what might happen in the future. And for that, we used two different socioeconomic paths, essentially middle of the road, and one where there's a fossil fuel development future for us, with 4 different date ranges. This then resulted in 32 models per native and in realized range. I'm not just going to show you all these maps because they don't mean much. There's just a bunch of colors essentially at this, there's so many of them. But if you look at the graphs, you can essentially see that there is a expansion or gain in terms of a potential invasive range for the species throughout the entirety of the potential future, except for one area in 2061 to 2080 for one fossil fuel potential future where there's 7% loss. But overall, I mean, this is all just projections, but overall there's an increase in potential invasive habitats that it can occupy in the future. So in conclusion, Toxomerus floralis has spread to 25 African countries since first detected in 2013. And then, of course, citizen science plays a key role in tracking and providing data for monitoring these invasive species. Just what I didn't mention is that all the citizen science data that we did use were verified, and we didn't use any GBIF records that weren't georeferenced or were georeferenced below, let's, for example, the 10-kilometer distance between the points, just so that we didn't have any overfitting of the model as well. And so Toxomerus floralis showed ecological plasticity and adaptability in being able to expand on and utilize new niches in invaded areas, while at the same time largely conserving its native climatic niche. And so future global climatic projections indicate that more suitable habitat is likely to become available in the native range and invaded ranges under future climatic scenarios. I'd just like to thank all of the above for support. Thank you.
Okay, thank you. That was our last talk for the session. Don't run away. John wants to say something after questions. Does anybody have questions for Burgert?
Thanks, Burgert. I wanted to ask, how did you do the niche overlap tests?
So the niche overlap tests were done with EcoSpat in R. So it's a package that allows you to test the niche overlap between. So what you essentially do is you take your your specimen species points distributions, as well as your bioclimatic variables, and then from it essentially compares the overlaps between the two, where the species occurs in both the ranges. And it then shows you whether the species occur in additional niche habitats of niche areas, essentially in the invaded range, and what the comparison is between the two to see if there's an overlap or there's stability or that sort of thing.
Okay, thanks.
Any more questions?
Sorry, I don't know anything about this insect. What is the effect of the invasion? Is it bad?
We don't know. It's very new still in terms of invading, and so we don't know what. I mean, we don't know what these two host plants are, but we don't know, there might be additional host plants that we're not aware of. It's a good model insect essentially to see how invasion, how it's spreading. But we don't know, for example, if there's any economic impact on it, from the invasion. Thank you.